In this session, we are going to investigate whether a function is a solution to an integral equation. By considering this example, what shall we call a solution to an integral equation? Hence or otherwise, show that y of s equal to cos s is a solution to the integral equation y of s minus integral from 0 to pi st y of t dt equal to cos s plus 2s. Let's start by defining the solution to an integral equation. The solution to an integral equation is a function y of s that makes an identity with respect to s, as we discussed in our previous video. Now let's consider the integral equation. And the function given us is y of s equal to cos s. To show that this function is a solution to this integral equation, let's consider the left hand side. And the function is given as y of s, which is equal to cos s. Since the unknown function appears under the integral sign, which is y of t, let's interchange the s to t's. And we are going to have our y of t to be equal to cos t. Now we have to substitute these two equations into this expression. So we're going to have cos s minus integral from 0 to pi st cos t dt. We have to solve this expression. And so let's start by considering the integral part, which is in such integration, we use integration by parts. But in this video, let's consider something called, let's use tables. Let's put our st here and cos c2 here. In this column, we are going to differentiate this side with respect to t until we get to 0. If we differentiate with respect to t, we are going to get s. With respect to t, we are going to get 0. This side, if we integrate cos t, we are going to get sin t. If we integrate sin t, we are going to get minus cos t. So that we map the sign. We will map the first term here to this side. So, and the sign, we alternate the sign from positive to negative. So positive plus negative plus. Now this integration becomes so st times or sin t, and here is positive. So have st sin t. This minus s times or minus cos t, so it becomes plus s cos t. And you are going to evaluate this at 0 to what? Pi. Wherever you see t, you replace it by what? Pi. You're going to have s pi sin pi plus s cos pi minus, whenever I see to replace the s into like a 0. We know that sin pi is 0. So here we are going to get sin pi. This sin pi is 0, and cos pi. We're going to have s cos pi. Here also give me 0, now plus minus s cos 0. Cos pi gives me minus 1. So s in bracket minus 1 minus x. Cos 0 gives me minus 1. So I'm going to get minus s, which will be equal to 2 minus 2s. So the whole of this integral is equal to what? Minus 2s. Now you have to substitute this into to this side. Left hand side we have cos s minus integral from 0 to pi st y of t dt. And this integration gave us minus 2s. So this is equal to we are going to get cos s, so minus again I go up, so here becomes plus 2s. So this is our left hand side. On the left hand side we had cos s plus 2s. Now let's consider the right hand side. On the right hand side we are having cos s plus 2s. Now, you could easily see that on the left hand side we have cos s plus 2s, and then on the right hand side we have what? Cos s plus what? 2s. So we are going to see that the left hand side is equal to the right hand side. Since the left hand side is equal to the right hand side, then y of s equal to cos s makes an identity with respect to s. Hence, this y of s is a solution to the integral equation y of s minus or integral from 0 to pi st y of t dt equal to cos s plus 2s. We're going to look at converting a Volterra's integral equation of the first kind to the second kind. Let's start by considering this. If you are given an integral this integral I is equal to integral from as ds f of st dt, and you pass it through an differential operator. Passing it through a differential operator, then this becomes I prime s. So this I'm going to apply differentiation under the integral sign. So this derivative, move another integral sign. dt. Now we need to differentiate the upper limit with respect to s plus d ds b of s. Then wherever you see the t, you replace it by the upper limit in the function. And subtract the derivative of the lower limit with respect to s. And you place the variable t with respect to the variable t with a of s. So this is the theorem we are going to use. That's the differentiation under the integral sign in converting Volterra's integral equation of the first kind to the second kind. Let's consider the Volterra's integral equation of the first kind. So it's integral from a to s. So this makes it to be a Volterra's integral equation. It is integral equation because the unknown function is under the integral sign. It's the first kind because the unknown function appears only under the integral sign. So we have to convert this into what? A second kind integral equation, which is a Volterra's integral equation. So now let's pass this through the differential operator. This and this and this to this. So we are going to have d ds, we will get f of s to be equal to, since it's a differential operator is a linear operator, that means that you can factor this one out. So we are going to have lambda d ds st. You could easily see that we have to apply differentiation under the integral sign as we did in our previous notes. It becomes f prime of s to be equal to lambda we are applying differentiation under the integral sign. So we first differentiate this function with respect to the s, the partial derivative of this. After that, we take the derivative of the upper limit and add it, and take this function, wherever you see the t, you insert the upper limit there, and minus the derivative of the lower limit, d ds, it will get a. Then wherever you see in this function, wherever you see t, you replace the lower limit there, which is a. So this is what we are going to get. Now a is a constant, so if we differentiate a, we are going to get 0. So our equation now becomes If we differentiate d ds, if we differentiate the s, you get what 1. So what remains is what k of s, comma s, y of s. This operator del s is the same as, so since it's a partial derivative, we can still write it as what k subscript of s of what s comma t, y of t dt plus what this. This is already giving us 0. So this is what we are going to get. Now let's make our what y of s the subject of the equation. So but let's divide each of the term by what k of s comma s. Now let's make this our subject of the equation. It becomes y of s by moving this one to the other side of the equation to be equal to so this is what you are getting. Now let capital F, which is a free term, to be equal to this free term. And our new kernel, let's make this as our new kernel. Let's name it as K1. Which is equal to can what? Bring the minus inside. So let's see minus. So this is our new kernel. Now let's replace these two equations into what? The equations here. The equation here. Capital F of S plus lambda. So, you can easily see that this is an integral equation. Yes, it is. And the limit is from what? A to S. So it is a Volterra's integral equation. Yes. And this is our free term, f of S. Alright. Now, this is our kernel. This is our new kernel K1 S comma T. Alright. And this our known function appears on the other side and also appears under the integral sign. So this makes this equation to be a Volterra's integral equation of the second kind. So we are able to convert this Volterra's integral equation of the first kind to what? Volterra's integral equation of the second kind. So we end this video by taking an example. Example like we will take the first kind and convert it to what? The second kind. Alright, I have an example here. Okay, we have to convert this Volterra's integral equation of the first kind to Volterra's integral equation of the second kind. So Volterra's integral equation because the what? The limit here is what? A variable, which is s, from a constant to a variable. And it's a first kind because the unknown function appears only under the integral sign. So we will pass this equation through a differential operator. We have ddx bracket sine s to be equal to ddx integral from 0 to s squared t y of t dt. So if we differentiate sine, we are going to get cos, which is called cos s. So from this side, you easily see that you have to apply what? Differentiation under the integral sign in our previous note. So we have to make it a partial derivative. Del the s to s squared t y of t dt plus the derivative of the what? The upper limit. This is our function. Wherever you see t, you replace it by what? The upper limit, s. You take the lower limit minus the derivative of the what? Lower limit. Wherever you see the what? T, you replace it by what? The lower limit, which is 0. Now, cos s will be equal to, if we differentiate this side with respect to s, we're going to get what? This is what? The s. If we differentiate s raised to the power 2, we're going to get what? 2s. If we differentiate the s here, we're going to get what? 1. So what remains is what? S squared times what? S. It will give me what? S cubed. Y of s. Now here is 0. All here becomes 0. So this is what we are having. Now let's make this y of s the solution of the equation by dividing each of the term by what? S cubed. And we're going to get this s here will cancel 1 over s here, so remaining what? S to the power of 2, which is so 2t divided by s squared y of t dt plus y of s. Now let's make this y of s the solution of the equation. We're going to get y of s to be, let's send this one to the other side, to be equal to cos s cubed minus two t divided by s squared y of t dt. Alright, you can easily see that this is what? The first kind. The unknown function appears only under the integral sign. By this side, you can see that the unknown function appears under the integral sign and also appears on the other side of the equation. So this makes the here to be what? Volterra's integral equation of the second kind, since we are integrating from 0 to s, and this is our free term, cos s divided by what? S because our free term. So we end, this is the end of this session.